Hi, this is Dr. Collins Jones. Welcome to segment 6 of my video series on measurement, significant figures, and basic data analysis. In this segment, we're going to cover the rules for determining significant figures. Let's start by reviewing the definition for significant figures. Significant figures are those digits in a measured value that include all the certain digits plus the final estimated or uncertain digit. So for example, suppose we weighed an item on the balance and the electronic balance display read 4,827.3857 grams. Okay? We know from our previous discussions that the final digit in a measured value is uncertain, right? And it is uncertain by at least 1 unit, right? So that means that this could be 4,827.3858, 4,827.3857, or 4,827.3856. That's our uncertain by plus or minus 1 unit. The balance is doing the estimate for us. So that's the uncertain digit. The last digit is always the uncertain digit. All of the other digits are the certain digits. These are the ones that we know for sure to be accurate, to be correct. All right. So again, though, all of the digits are recorded as part of the measurement. What you see on the display, an electronic balance, a pH meter, a conductivity meter, the spectrophotometer, whatever it is that you're using to make your measurement, you record all of the digits that are displayed. Okay. To determine the number of significant figures in a measurement, you simply count all the digits. So here's our measurement, and you just count the number of digits. 1, 2, 3, 4, 5, 6, 7, 8. Okay? So the measurement has a total of 8 significant figures. This includes, that tally includes the uncertain number. And again, the last digit, the 7, is estimated or uncertain, but it is part of the number of significant figures that are present. So we have 8 significant figures. Let's look at a few rules here to help us through sort of less clear data recordings. So first, all non-zero digits in a measurement are significant. Anything that's not zero is considered to be a significant digit. All right, so here we have 8 significant digits. We just count. Again, 1, 2, 3, 4, 5, 6, 7, 8. Didn't I make that easy? All right. Zeros in between non-zero digits are significant. So all of these zeros, they are significant because they are part of the measurement. So this has 10 significant figures. This measurement has 10 significant figures. All right. Leading zeros, that is zeros in front of the number, right, are not significant. So if the zeros are used to indicate the size of the measurement, to place the decimal point, these zeros are not significant. So this measurement only has 1 significant figure. Similarly, these zeros are not significant, but now we have 4 significant figures. Okay? All right. Terminal zeros. These are zeros at the end of the reported measurement. If they are to the right of the decimal point, they are significant. All right. So here we have 123.000, right? These zeros are significant. So we have a total of 5 significant figures. Here we have zeros in front of our significant digits and after our significant digits. So the leading zeros that are used to place the decimal point, these are not significant. But these zeros, right, are significant because they are to the right of the decimal point. So here we again have 5 significant figures. So that should be pretty straightforward, pretty easy. The ambiguous case is when we have something like 875,000, okay? And again, notice I've not put any units here, so technically these are not measurements, but I just wanted to really focus on the digits, not the units. All right, so 875,000. There's no decimal point there, so we don't know if those zeros are simply telling us the size of the number, or do we actually measure this to be 0. All right, so that means, at least when you have me for an instructor, that means that though we don't know if those zeros are significant because there's no decimal point. So that means that we could have 3, right? 875. Those are significant. Those are non-zero digits. So those 3 digits are absolutely significant. So we have a minimum of 3 significant figures. But we could have 4, or we could have 5, or we could have 6 total significant figures. We don't know which, if any, of these zeros are significant. So if you were taking an exam from me and I gave you a problem like this, the answer would be 3 or 4 or 5 or 6 significant figures. It's ambiguous. We don't know. You'd have to write all those down. And again, it's only ambiguous because there's no decimal point here, right? If this was 875.000, then there would be 6 significant figures. That would be the only answer. Okay? All right. Trailing zeros, as in something like 2,500 grams, may either be a placeholder to indicate the size of the measurement, or they may be significant. So they're ambiguous. To indicate which trailing zeros are significant, the measurement may be expressed in scientific notation or prefix notation. All right, and so we'll illustrate this in a little more detail on the next slide. But some companies, institutions, organizations, this is sort of old school, but I've still seen it, right, as recently as 2024, place a bar over the uncertain zero. This is not universally accepted. It is rarely used in biotech, but I just want you to know about this. So in this example here, here's our bar, 2,500. We've put a bar over this zero, so that means this zero is significant, but this zero is not significant. So we have 3 significant figures. If we're going to express this in scientific notation, it would be 2.50 times 10 to the plus 3. In a previous segment, I indicated this, but this is a good place to sort of remind you. More recently, we purchased some new electronic balances, and in the electronic balance display, in the digital display, the balance software actually puts a bracket over the uncertain digit, just like that. And so here's an actual picture of the balance, and you can see right there the last digit, that 8, is uncertain, and the electronics, the software in the balance has actually indicated it's uncertain by putting a bracket over it. Okay? When you're at a company, the SOP or the batch record should specify the required number of significant figures and the format in which to document them. So sometimes they actually just put a box. If there's 5 significant figures, there's 5 boxes to fill in, and they might also put the decimal point in between. Okay, so I ask here, who writes new SOPs and batch records? Eventually, you will be one of those people writing the new SOPs and batch records. So you're going to have to remember how to do significant figures. Okay, all right. How to deal with ambiguous zeros. Let's use our 2,500 grams as an example once again. Right? If we wrote this as 2.5 times 10 to the third grams, or 2.5 kilograms, because remember, kilo represents 10 to the 3, right? This would indicate 2 significant figures. If we write it as 2.50, right, either times 10 to the third or 2.50 kilograms, this tells us we have 3 significant figures because this 0 is on the other side of the decimal point. It's to the right of the decimal point. And if both zeros were significant, we would write this as 2.500 times 10 to the third, or 2.500 kilograms for 4 significant figures. Now, it's important to remember that oftentimes when you're entering this into your calculator, if you put in 2.500, the calculator usually drops those 2 zeros to save memory space. They're still there, though. In the real world, they're still there. But your calculator may drop trailing zeros because that's how they save memory. Right? If all 4 digits, right, 2,500, the 2 zeros were also significant. So if all 4 digits were significant, we could also put in a decimal point, right? And that would tell us that both of those zeros are significant. So always, always remember to adhere to the data sheet or the batch record recording requirements. All right, exact numbers. Exact numbers or coefficients, and coefficients in a balanced equation. So we have coefficients, and we're going to consider those to be exact numbers. Counted numbers, conversion factors, and constants should not be used to determine the number of significant figures during calculations unless the constant is calculated. Okay, so things like 50 colony forming units, a dilution factor of 1 to 50, right? A conversion factor, one absorbance unit is 1.23 grams per mil, right? Or conversion factors, 1 inch equals 2.54 centimeters. Generally, we don't consider those to be included when we determine significant figures in a calculation. There may be exceptions, so be sure to ask your instructor, but for things like conversion factors, right? 1 AU equals 1.23 grams per mil, or 1 inch equals 2.54 centimeters. Usually we can actually, if we look this up on the internet, we can get a lot more digits to increase the number of significant figures. So at least when I teach these courses, I say don't consider the significant figures in terms of conversion factors, but check with the SOP, with the batch record, with your instructor. Okay, so again, these are exact numbers, and an exact number can be considered to have an unlimited number of significant figures. All right, let's do some practice. Let's see how well you did with this, okay? So here are some examples. I'm going to count to 3, maybe 5, while you pause the video and see how you do here. Okay, first one, 119.1 mils. Okay, 4 significant figures. The uncertain digit is the 1. 8,525.6 grams. 5 significant figures. The uncertain digit is 6. 0.139 kilograms. The 0 is to the left of the decimal. It is placing the decimal, so there are only 3 significant figures, 0.139, and the 9 is the uncertain digit. 36.2 degrees centigrade. 3 significant figures, the 2 is uncertain. 30.4 mils per minute, right? That 0 is in between 2 significant digits, so that 0 is significant. So there are 3 significant figures, and the 4 is the uncertain digit. 20.00 mils, all right? So those zeros are all significant because of the decimal point. So this has 4 significant figures, and 0, the last 0, this 0 is significant. 250 centimeters, right? We don't know if this 0 is significant or not. This is ambiguous. So this would have 2 or 3 significant figures, and the uncertain digit then would either be 5 or 0. 100 data points. This is a counted, right? A data point is an exact number, so the uncertain digit is not applicable here. All right, and then, oh my gosh, that's a big number. What is that? 4,102,300.100 nanograms. Okay, all of those zeros are significant. So this has 10 significant figures, and the last 0 right here, is significant. And so if the data point question tripped you up, then this one should not. 72 mice, that's an exact number, so there is no significant figure here. There is no uncertain digit. There is no uncertain digit when we have counted numbers. Okay, recording measurements. We just want to emphasize this. Record the correct number of significant figures for all measurements. Even if the number of significant figures varies from one measurement to the next, record all the digits that you see in the display. Okay? Be sure to include the correct units. Remember, a measurement consists of a number plus a unit, and then follow our good documentation practices using Alcoa. All right. Finally, another little practice table for you guys to fill out. I'm going to count to 3 again while you pause and see how you do with this. And this sort of summarizes several segments at once, and then I'll fill in the answers, and that will be the end of segment 6. Okay, back. Here we go. So first we're asking you to convert this from grams to milligrams, then tell us what you think the measuring instrument is to measure this value, then tell me the number of significant figures and the uncertain digit. Okay, so if we convert this to milligrams, it's going to be 38.1 milligrams. The measuring instrument here would be a balance because it's a weight. There's 3 significant figures and the uncertain digit is 1. 892 mils. Convert this to liters. So this would be 0.892 liters. We would use a 1 liter graduated cylinder. There are 3 significant figures here, and the 2 is the uncertain digit. 75 microliters to mils. This would be 0.075 mils. Okay, looks like for this we would use a P200 or a P100 micropipetter. There are 2 significant figures here, and 5 is the uncertain digit. 6.085 kilograms. This would be 6,085 grams. We would use an electronic balance that is able to weigh kilogram quantities. There are 4 significant figures here, and the uncertain digit is again 5. 700.0 milliliters converted to liters. So this would be 0.7000 liters, and we have to retain the zeros because they're all significant since we have a 0 to the right of the decimal point. So we're going to measure this again using a 1 liter graduated cylinder. There will be 4 significant figures here, and the last 0, this 0 or this 0 is significant. 3.8 mils to microliters. This would be 3,800 microliters. Okay, but here we only have 2 significant figures. So first of all, we would measure this using a 5 mil serological pipette. There are only 2 significant figures here, right? And the 8 is the uncertain digit. 50 milligrams to grams. This would be 0.500 grams. And again, we need to retain these zeros because the decimal point tells us that both of these are significant, right? And so again, electronic balance, 3 significant figures, and the 0, right? This last 0 right here, this 0 or this 0 is significant, and it's uncertain because it's the last digit. Okay, 408.1 grams to kilograms. This is 0.40810 kilograms. We would measure this using an electronic balance. There are 5 significant figures here, and again, the last digit is 0, so that's the uncertain digit. The last digit is 0, that's the uncertain digit. 0.00153 mils to microliters. This would be 1.53 microliters. Okay, we would use a P2 pipetteman, and these zeros are not significant, right? They're used to place the decimal point. So here we're going to have 3 significant figures, and the 3, this 3 right here is the uncertain digit. And then 0.369 mils to microliters. This would be 369 microliters. We would use a P1000 to measure this. There are 3 significant figures here, and the 9 is the uncertain digit. So I hope that helped. I hope you did well on this little exercise, and that is the end of segment 6.